So in this lecture, I've got two kind of classic geometry problems involving circles for us to take a look at. The first one here, we have a skating rink, and it's made up of two semicircular sections kind of glued onto the short ends of a 50 by 20 foot rectangle. And I want to know what are the perimeter and surface area of the rink. So whenever I have a question like this, the first thing I'm going to do is I'm going to draw a picture, right, to get a visual idea of what it is we're talking about. So I'm going to start by drawing this rectangle. The rectangle is going to be 50 feet on the long sides and 20 feet on the short sides. Then I'm going to draw the two semicircular pieces. So those are going to go on the 20-foot sides. So it's going to look like this. Now this is the part where students start running into trouble when we're trying to find that perimeter. Remember, the perimeter is the distance around the outside. If you were to get out and you were to walk around this figure, what distance would you travel? Well, the problem students have is they try to include that 20-foot distance in the calculation. And yes, we need that 20-foot number. It's going to be part of the calculation. But we're not actually going to add 20 feet at any point, because when you get to this corner here, you don't make a hard left turn and start walking those 20 feet. You keep going around the circle. Right, so what I'm going to do is I'm going to take out those 20 feet segments and just replace them with dash lines, kind of as a way to emphasize that, yes, I need that number, but they're not actually going to be part of the perimeter or part of the distance somebody would actually walk. Okay, so to find the distance around, it's made up of four pieces. It's made up of the two 50-foot sections plus the two semicircular pieces. But remember, if we put two semicircles together, we get a whole circle. So ultimately, you're going to have to walk around an entire 20-foot diameter circle during the course of walking around the rink. We have a formula right for the circumference, the distance around a circle. That's pi times the diameter. Since the diameter here is 20 feet, this is 20 pi. We add the two numbers together. The perimeter is 100 plus 20 pi feet. Now that's the exact value, and to the mathematician like myself, that's a perfectly good answer. It's not the kind of answer, for example, that you want to take to the County Planning Commission. Right? It's not going to be a happy conversation if you go and try to tell them you're going to build a skating rink that's 100 plus 20 pi feet around. They want a decimal value. Right? So to turn this into a decimal value, I would say 100 plus 20 times, just use 3.14. That's two decimal places, should be plenty of accuracy for this kind of question. So this is 100 plus 62.8 feet. So the total perimeter of our rink would be 162.8 feet. And don't forget the units there at the end when you're talking about a practical situation. All right, so how about the surface area? Right, an important question. If you're thinking about how much water it's going to take, for example, to fill this stuff up, and then you freeze it over and people can go skating. So we're going to do the same thing with the area. The area is equal to the area of the rectangular part plus the area of the two circular parts. Let's put a little circle. So the area of the rectangular parts are easy. This is 50 times 20. It's a rectangle, so it's length times width. And for the area, I'm going to use the same argument. I'm taking two 20-foot diameter semicircles, putting them together. That gives me the total area of a whole 20-foot diameter semicircle. Now here's where you got to be careful. Students often trip over this. Remember, the formula for the area of a circle is pi r squared, not pi d squared. Right? So we need the radius here. So this is going to be pi times the radius, that's half the diameter. So that's going to be 10 squared. Right, 50 times 20, that's 1,000. 10 squared is 100, so this is 100 pi. And again, really not going to want pi in the answer for a practical kind of question. So we'll make this 1,000 plus 100 times 3.14. That's 1,000 plus 314. So our total area is going to be approximately 1,314 square feet. So for our second question here, I've got this situation where we have uh, one thing inscribed in another thing inscribed in another thing. To inscribe one object in another, it just means to draw it inside in such a way that they're just touching at the edges. You see that here with the circle and the square. I'm going to assume they're just touching here at these four corner points. Same thing with the triangle and the circle. So what else do we know? There, you've got these inscribed parts. It's a right triangle. Now, whoever drew this diagram didn't write this in, but I'm going to go ahead and do it. Let's put the symbol for a right triangle there. So I know that that's a right angle. So a right triangle inscribed in the circle whose upper side passes through the center. And the radius of the circle is 10. All right, so if the radius is 10, then this is going to be 10 feet. And this is going to be 10 feet. And this distance here, because the triangle is just touching the circle there, that's also a radius, which means that's going to be 10 feet. Okay, excellent. I think this is all I'm going to need to know to figure this out. All right, so now one more piece. The length of a side of the square here, that's equal to the diameter of the circle. Diameter of the circle is 20 feet. All right, so what's my area going to be? Well, I'm going to start off with the area of the square. Then I'm going to subtract out the area of the circle because I don't want that white part. Then I'm going to add back in the area of the triangle. All right, the area of a square, that's just side length times width, just like a rectangle. So that's going to be 20 times 20 minus the area of the circle, that's pi r squared. The radius is 10, so this is 10 squared times pi. Finally, the area of the triangle. Area of a triangle is 1/2 the base, which is the diameter. So that's going to be 10 times the height, which is the radius that I drew in. That's another 10. Excuse me, it's not 10. Diameter is 20. All right, now it's just an arithmetic problem. This is 400 minus 100 pi plus 1/2 times 20 is 10. 10 times 10 is another 100. So this is 500 minus 100 pi. And what are our units here? We're doing this in inches. I put feet in here. It should be 10 inches. So this is 500 minus 100 pi square inches. And this isn't so much a practical problem. It's really just kind of an abstract math problem. So it would be perfectly okay for us to leave it at that point. But if you wanted to go forward, certainly you could. You could make this 500 minus 100 times 3.14, which is 500 minus 314, which is, I think, 186 square inches. So next section, we're going to switch up. We're going to do something a little different. Everything we've talked about so far has taken place in a plane, on a flat surface like a piece of paper. In the next lecture, we're going to add a third dimension. We're going to talk a little bit about shapes that are three-dimensional, what in geometry are called solids.